Right now, your kidneys are deliberately starving themselves of oxygen just to survive the sheer overwhelming volume of blood your
Yeah.
heart is blasting into.
Yeah, it sounds like a total paradox, right? I mean, they receive up to 25% of your total cardiac output. That is an absolutely massive share of your blood flow at any given second.
Yeah.
Yet, the complex internal vascular networks are structured so that the deepest parts of the kidney, well, they basically operate on the absolute razor's edge of hypoxia.
It's wild. Welcome to this deep dive, everyone. Our mission today is to completely deconstruct the dense, honestly incredibly intricate source material we've gathered on renal physiology.
Definitely.
We're getting way past the basic textbook summaries of, kidneys as waste filters. We are looking at the actual hemodynamics, the cellular engineering, and what happens when we use pharmacology to hack the system.
Yeah.
Or what happens when the system undergoes a catastrophic cascade of failure.
Because, treating the kidney like a passive plumbing system fundamentally misunderstands what it does. It's an active, aggressive master regulator. It dictates your systemic blood pressure, your skeletal density, and even your red blood cell count.
And to really grasp how this master regulator works, I think the most fascinating entry point from our sources is to look at how we intentionally break its rules.
Right.
We use diuretics to essentially weaponize the kidney's own mechanisms to dump fluid. And the golden rule in renal physiology seems to be water follows salt.
Precisely. Osmotic pressure dictates fluid movement. Most diuretics, the drugs we use to manage severe edema or hypertension, they don't actually target water directly.
They go after the salt.
Exactly. They target the cellular transport proteins that reabsorb sodium from the renal tubules back into the blood. So if you chemically block those sodium channels, the sodium just remains trapped in the tubular lumen.
Which means the water gets trapped too.
Right. Because of osmotic forces, that sodium physically holds on to the water molecules, preventing the body from pulling them back in. It literally drags the water out of you.
The text highlights loop diuretics, like furosemide, as the absolute heavy hitters here.
Yeah.
And reading the mechanism is just crazy. They specifically target the thick ascending limb of the loop of Hendel. They don't just stop a little sodium, they block the sodium-potassium chloride cotransporter entirely.
Which is absolutely devastating to the kidney's normal fluid retention strategy.
Wow.
Yeah, that specific cotransporter is what the kidney uses to pump salt deep into the surrounding tissue, creating this highly concentrated, super salty environment in the renal medulla.
And that salty environment is what pulls the water out later.
You got it. That's what naturally pulls water out of the collecting ducts later on. By paralyzing that transporter, loop diuretics just destroy the concentration gradient. The kidney can suddenly dump up to 30% of the entire glomerular filtrate straight into the bladder.
That is massive.
It is. You can increase urine output 25-fold in a matter of minutes.
But the sources also cover carbonic anhydrase inhibitors, which take a totally different route, right?
Yeah.
They block bicarbonate reabsorption in the proximal tubule. But the collateral damage there seems intense.
Yeah.
You end up in a state of metabolic acidosis because you're literally peeing out your blood's vital base buffer.
Exactly. It's a blunt instrument. And then you have the potassium-sparing diuretics. This is crucial because standard loop diuretics force you to excrete massive amounts of potassium along with the sodium.
Which is bad.
Very bad. It can cause severe cardiac arrhythmias. Potassium-sparing drugs, like spironolactone, they block the action of the hormone aldosterone further down the line, ensuring you lose the salt and water, but keep the potassium safely in your serum.
Okay, let's unpack this, because here is the mechanism that really caught me off guard. Is sodium essentially the Pied Piper, and the water molecules are the rats just following it out of the body?
That is a perfect analogy, actually.
Yeah.
Yes.
But then you take a powerful loop diuretic, right? You start flushing out liters of fluid. But after a few days, the diuretic effect just plateaus. The drug doesn't just keep working until you dehydrate into a husk. Why does the diuretic stop driving fluid loss?
Well, what's fascinating here is how the body's compensatory mechanisms fight back against the diuretic. You've triggered the kidney's failsafes. The moment that systemic fluid volume drops, your overall blood pressure drops with it.
Right.
And there's a specialized cluster of cells in the kidney called the macula densa that senses this pressure drop and the altered sodium delivery. The kidney basically sounds the alarm and dumps the enzyme renin into your bloodstream.
Ah, the renin-angiotensin-aldosterone system. It's like the ultimate override switch.
Right. Renin triggers the production of angiotensin II, which is an incredibly potent vasoconstrictor. It aggressively tightens your blood vessels, particularly the efferent arterioles exiting the kidney's filters.
So it's pinching the exit pipe.
Exactly. This artificially props up the filtration pressure inside the kidney, forcing it to hold on to whatever fluid is left. The body essentially fights the drug to a standstill.
Wow.
You end up establishing a new equilibrium where your fluid intake perfectly matches your output again, just at a significantly lower overall fluid volume, which therapeutically is exactly what you want for a patient with congestive heart failure.
So the system regulates itself perfectly. It proves how aggressively the body defends its homeostasis. But that's a controlled pharmacological hack. What happens when the blood pressure drop isn't from a carefully dosed pill, but from a massive trauma, say a severe hemorrhage?
Well, then we leave the realm of controlled homeostasis and enter acute kidney injury, or AKI, specifically prerenal AKI, which is caused by a sudden, drastic drop in blood supply.
I was trying to map out the 3 types of AKI from the text. I was thinking of it like a factory. So prerenal is the factory losing its supply chain, interrenal is machinery catching fire, and pulsional is the delivery trucks backing up at the exit gate.
That's a really good starting framework, but let's make it a bit more anatomically precise. Because in intrarenal AKI, the machinery isn't just catching fire, it's like actively being dissolved or jammed by friendly fire.
Oh, wow.
But let's start with your supply chain issue. Prerenal. If you hemorrhage, the blood flow to the kidney plummets. To survive, the kidney initiates an extreme ischemia protocol. The glomerular filtration rate, or GFR, drops drastically.
Wait, if the filtration rate drops, doesn't that mean metabolic toxins are rapidly accumulating in the blood? How is shutting down the filter a good survival trade-off for the body?
It's pure triage. You see, the active transport of sodium out of the tubules requires massive amounts of ATP, meaning it requires immense amounts of oxygen. If you drop the filtration rate, less sodium enters the tubules, which means the cells don't have to work as hard to reabsorb it.
Oh, so the oxygen demand plummets.
Exactly. The kidney essentially puts itself into a metabolic hibernation. It sacrifices systemic blood purity to prevent its own tissues from immediately dying of hypoxia. It can basically survive on just 20 to 25% of its normal blood flow.
It survives the day to deal with the toxins next week.
Exactly. But if we move to your second category, intrarenal AKI, where the damage originates inside the kidney tissue, that hibernation trick doesn't work. Take acute glomerulonephritis, you can get a simple strep throat, recover, and then 1 to 3 weeks later, your kidneys start failing.
Because of the immune complexes. The body's own defense mechanisms become the weapon.
Right. Your immune system generates antibodies to fight the streptococcal bacteria, but sometimes these antibodies bind with the bacterial antigens to form large, insoluble immune complexes. They circulate in the blood and get physically wedged into the delicate basement membrane of the glomerulus.
And the immune system attacks them there.
Yes. It detects them there and unleashes a massive inflammatory response, attacking the kidney's own filtration barrier. It severely damages the podocytes, the specialized cells wrapping the capillaries, causing red blood cells and massive amounts of protein to spill directly into the urine.
Right, and the sources note that intrarenal AKI can also be triggered by exogenous toxins. Antifreeze, which is ethylene glycol or heavy metals, they cause acute tubular necrosis. They literally kill the epithelial cells.
This raises an important question, though, about how the body handles these toxins. Why are the tubular epithelial cells so uniquely vulnerable to these poisons compared to the rest of the body?
Oh, is it because they're concentrating it?
It comes right back to their function, concentration. As the filtrate moves through the tubules, the epithelial cells are furiously reabsorbing water back into the blood. As the water leaves the tubule, the concentration of whatever is left behind, like the ethylene glycol metabolites, skyrockets.
So they're poisoning themselves.
The cells are essentially distilling the poison, delivering a hyper-concentrated lethal dose right to their own membranes. The cells die, slew off into the lumen, and physically plug the tubes.
Which brings us to the delivery trucks backing up. Whether it's cellular debris plugging the tubules or a massive kidney stone blocking the ureter, that's postrenal AKI. But regardless of which of the 3 types you have, the immediate danger of this sudden stop isn't just fluid overload, it's the potassium threat, right?
Hyperkalemia, yes, because the kidneys are the primary route for excreting dietary potassium. If filtration stops, Potassium accumulates rapidly in the extracellular fluid.
The numbers in the text are terrifyingly small. Normal potassium is around 4 milliequivalents per liter. If it rises to just 8, which is only twice the normal level, it's fatal. Why is such a tiny absolute increase so deadly?
Because of the resting membrane potential of your cardiac muscle cells, the voltage gradient across the cell membrane relies heavily on the ratio of intracellular to extracellular potassium.
So it messes with the electricity of the heart.
Exactly. If the extracellular potassium doubles, it partially depolarizes the resting membrane potential. The heart muscle becomes hyperexcitable at first, but then rapidly loses the ability to reset its action potential. It leads to ventricular fibrillation and cardiac arrest.
Wow.
Complete anuria, so zero urine output, leads to death in 8 to 14 days without intervention, usually from a hyperkalemic cardiac event.
It's an incredibly fast, violent crash. But that's acute injury. The source material spends an equal amount of time on the exact opposite scenario, the slow, silent erosion of chronic kidney disease, or CKD.
Right. If AKI is an abrupt mechanical failure, CKD is a slow-motion architectural collapse. It is the progressive, irreversible loss of functional nephrons over months and years.
And the clinical presentation of this is mind-blowing. The text explicitly states that a patient will generally not show serious clinical symptoms until 70 to 75% of their nephrons are completely destroyed.
Yeah, it's hidden.
Here's where it gets really interesting. You can maintain perfectly normal body fluid volumes with just 25% of your total kidney mass left. How is it physically possible to lose 3/4 of a vital organ and not notice?
Through an incredibly aggressive but ultimately tragic physiological adaptation. It's known as the vicious cycle of CKD. When a nephron dies, whether from diabetes, hypertension, or inflammation, the surviving nephrons immediately sense the decreased overall clearance.
Right.
They react by undergoing hypertrophy. They physically enlarge.
So the afferent arterioles feeding them vasodilate, flooding the surviving filters with more blood to pick up the slack. They become like these super worker nephrons.
Exactly. Each surviving nephron significantly increases its individual filtration rate. But there's a devastating biomechanical cost. To force that much extra fluid through a single filter, the intraglomerular pressure has to rise dramatically. This chronic high-pressure state subjects the delicate mesangial cells and capillary walls to immense shear stress and mechanical stretch.
So by stepping up to do the work of 4 nephrons, the survivor is physically tearing itself apart.
It induces endothelial damage. The physical stress triggers the release of profibrotic cytokines. Over time, the flexible filtering tissue is replaced by hard, non-functional scar tissue, which is a process called glomerulosclerosis.
So the compensation itself is a death sentence. The harder they work to save you, the faster they scar themselves into oblivion.
It's the tragedy of the superworker nephrons. It is a self-perpetuating cycle. Once a critical mass of nephrons is lost, the hyperfiltration of the remaining ones guarantees their eventual destruction, regardless of what caused the initial injury.
And the original culprits driving that initial injury are overwhelmingly metabolic. The text points out that diabetic nephropathy accounts for 45% of end-stage renal disease. Hypertension is 27%.
Both heavily driven by obesity, yeah.
Right. The chronic high blood glucose of diabetes literally glycates the proteins in the efferent arterioles, stiffening them and artificially driving up that internal glomerular pressure. Add systemic hypertension on top of that, and you are just supercharging the mechanical trauma.
And, we can't ignore simple senescence. Normal aging naturally costs us about 10% of our functional nephrons every single decade after we hit age 40. We are all slowly losing capacity.
So as these superworkers are grinding themselves to death, how does the system breakdown actually manifest? Like, what does the physiology look like as you approach end stage?
One of the earliest clinical markers is a phenomenon called isostenuria. As the nephrons die, the surviving ones are processing fluid at such a high velocity that the complex mechanisms for reabsorbing water or secreting waste simply can't keep up. The tubular fluid flows too fast.
So they lose control over the concentration.
The kidney loses the ability to concentrate or dilute urine entirely.
The specific gravity of the urine just locks in at about 1.0 Ren 0, which is identical to the original plasma filtrate. You could completely restrict a patient's water intake for 12 hours, and their urine concentration wouldn't increase. The concentration gradient in the renal medulla has essentially been washed out.
Yeah, and as the physical filters sustain more microscopic tears, they lose their selective permeability. We see this acutely in conditions like nephrotic syndrome, The filtering membrane becomes too permeable.
Right.
There's a specific pathology mentioned in our sources, minimal change nephropathy, which frequently affects young children. The podocytes in the glomerulus lose their negative charge barrier. Normally, that negative charge repels plasma proteins, which are also negatively charged.
Like magnets repelling each other.
Exactly. But without it, massive amounts of albumin leak into the urine. A patient can lose up to 40 grams of plasma protein a day.
Which fundamentally ruins the body's fluid distribution. Because those plasma proteins provide the colloid osmotic pressure for the blood. They act like molecular sponges holding water inside the vascular space. You lose the protein, you lose the sponge effect. The water leaks out of the capillaries and pools in the interstitial spaces, causing massive whole-body edema.
The fluid shift is profound because the blood can't hold on to its own water. But as the total nephron mass drops below 20%, we enter the uremia cascade. And this is where we see the systemic endocrine failure of the organ.
This was the biggest paradigm shift for me. I always associated kidney failure with just a buildup of urea and metabolic waste. But the cascading endocrine failures are just as lethal. Wait, so if I have CKD, my bones get weak, and my red blood cells drop. I never would have connected my kidneys to my skeleton.
If we connect this to the bigger picture, it makes sense. Because the kidney isn't just a waste chute, it's an endocrine organ constantly signaling the bone marrow and intestines. It's a sensor and a hormone factory. Specialized peritubular cells in the kidney constantly monitor blood oxygen levels.
Okay.
When they detect hypoxia, they secrete erythropoietin, or EPO. That EPO travels to the bone marrow and prevents the apoptosis, the programmed cell death of red blood cell progenitors, allowing them to mature.
But if the kidneys are scarred?
Exactly. As the kidney tissue scars over in CKD, those peritubular cells die. EPO production plummets, the bone marrow stops producing sufficient red blood cells, and the patient becomes severely anemic.
And the skeleton connection is equally surprising. I always thought vitamin D was purely a skin and sunlight mechanism. But the text details how the kidneys are required for the final activation step.
Correct. The skin synthesizes cholecalciferol, and the liver modifies it, but it remains biologically inactive. It's the proximal tubule cells in the kidney that perform the final hydroxylation step, converting it into active calcitriol.
Wow.
And without active vitamin D, your gastrointestinal tract simply cannot absorb calcium from your diet no matter how much you eat. So your blood calcium levels drop, your parathyroid gland detects the deficit, and it panics. It releases parathyroid hormone to desperately pull calcium directly out of your bones to keep your serum levels normal. Over time, that completely demineralizes the skeleton, leading to osteomalacia, or weakened bones. Your bones literally dissolve to maintain blood calcium.
It proves how integrated the system is. We've traced how chronic diseases like diabetes slowly dismantle this network, but our sources also highlight what happens when the blueprint is flawed from birth.
Right, the genetic tubular disorders. These are fascinating because they isolate exactly how crucial individual transport proteins are. The text covers Little syndrome, which causes severe hypertension because the sodium channels in the collecting tubule are stuck in overdrive. But what does stuck in overdrive actually mean at the cellular level?
It's a mutation in a single missing gene, basically affecting the epithelial sodium channel, or ENS. Normally, these channels are dynamically regulated. The cell constantly inserts them into the membrane and then degrades them to precisely control sodium uptake. In Little syndrome, a genetic mutation alters the structure of the channel protein so the cellular machinery can't bind to it to degrade it. The channels accumulate permanently in the membrane. They continuously pull sodium, and therefore water, into the blood, mimicking a state of massive aldosterone excess, even though actual aldosterone levels are near zero.
And on the opposite end of the spectrum is Fanconi syndrome, where almost everything goes wrong at once. It's a generalized defect where the tubules fail to transport almost anything properly. The cells fail to transport glucose, amino acids, phosphate, bicarbonate. It all just spills out into the urine.
Which leads to metabolic acidosis, dehydration, and severe growth retardation in children. But whether the destruction comes from a genetic defect, acute toxicity, or the slow superworker burnout of CKD, you eventually reach a state of end-stage renal disease. The biological hardware has totally failed.
And that's when we transition from biology to applied physics. We use dialysis, the artificial kidney, to replace a master regulator.
Right. When ESRD hits, we use a machine. Hemodialysis relies on a very simple physical principle acting across a synthetic, thin, porous cellophane membrane. The patient's blood flows on one side of this porous barrier, and a highly engineered dialysate fluid flows on the other.
So what does this all mean? I was trying to visualize this earlier. It's like washing a dirty sponge, right? You have to put it in clean water, not water that already has the same amount of dirt in it. It's purely passive physics, just diffusion gradients.
Exactly. It's governed by Fick's law of diffusion. To maximize the efficiency, modern dialyzers use countercurrent flow. The blood is pumped in one direction, and the dialysate is pumped in the exact opposite direction. This ensures that a steep concentration gradient is maintained across the entire length of the membrane.
Because if they flowed in the same direction, the concentrations would just equalize halfway down the tube and the cleaning would stop. So you engineer the dialysate to have 0 urea and 0 creatinine. The high concentration of those toxins in the patient's blood violently diffuses across the cellophane into the empty dialysate. But how do you prevent the good stuff from diffusing out, too?
By meticulously matching the dialysate to the ideal concentration of human plasma. The fluid is preloaded with the exact physiological levels of sodium, chloride, and potassium. Because the concentration is equal on both sides of the membrane, there is 0 net diffusion of those vital electrolytes. You strip out the waste while leaving the essential ions perfectly balanced.
It's a brilliant hack. The text says a dialysis machine can actually clear urea at a rate of about 100 to 225 milliliters per minute, which is technically faster than 2 perfectly healthy kidneys. But the catch is the time limitation.
It's a massive limitation. The biological kidney maintains exquisite homeostasis 24 hours a day, continuously reacting to every meal, every glass of water, every change in posture. A dialysis patient is only hooked up to the machine for 4 to 6 hours, maybe 3 days a week. In between sessions, their fluid and toxins are constantly building up.
Plus, the cellophane membrane can't secrete hormones. It cannot replace things like erythropoietin, so dialysis patients need synthetic injections to survive the anemia. It can't activate vitamin D, so they need calcitriol supplements to stop their bones from dissolving.
Right. It's an incredible feat of engineering that keeps millions alive, but it really highlights how flawlessly the biological kidney works 24/7 without us even thinking about it. It is arguably the most sophisticated chemical processing plant in the known universe, packed into 2 organs the size of a fist.
So as we pull all of these concepts together, look at the journey we've just charted. We started by looking at how loop diuretics physically hack the system and dismantle the kidney's medullary concentration gradient to force water out of the body. We examined how, during severe trauma, the kidney will essentially put itself into a hypoxic coma, surviving acute shocks by dropping its own filtration rate.
Yeah.
We unpacked the tragic irony of chronic kidney disease, where the surviving nephrons physically stretch and enlarge to process more blood, only to trigger a silent, compensating, vicious cycle that scars them to death. And finally, we looked at our cellophane membrane backups.
It really requires a profound appreciation for the invisible, tireless work your 2 million nephrons are doing right now.
It absolutely does.
Yes.
Right now, they are dynamically adjuncting your internal chemistry without a single conscious thought from you. But looking at all this data, there's one provocative thought I want to leave you with, something to mull over that pushes beyond current medical practice. We talked extensively about the vicious cycle of CKD. We know that when a nephron dies, a specific paracrine signal tells the surviving nephrons to physically grow, to undergo hypertrophy, and massively multiply their individual workload to cover for the dead ones.
Right.
In disease, that high-pressure compensation ultimately destroys them. But think about the sheer power of that cellular learning. The kidney possesses a latent, built-in mechanism to rapidly scale up its functional capacity on demand. So what are the ultimate limits of this cellular learning in other organs?
Oh, wow.
Could we one day figure out how to fully map that exact signaling pathway? Could we chemically harness that regenerative superworker signal to heal the body without triggering the vicious cycle of high pressure that destroys it? If we could isolate the signal for growth from the mechanical stress of hyperfiltration, we might not just treat kidney disease with cellophane and diffusion gradients. We might actually unlock the hidden gears of the master regulator and command it to rebuild itself. Imagine the possibilities.